All right, this is example 10 of tracing recursive algorithms. So we've got a function called M5. It takes in two ints, A and B. So we are definitely going to have to keep track of A and B. We're sending 5 and 3. And when we send 5 and 3, A is not 0, so we're not returning 1. We're going to the else. What we're returning for this recursive instance of M5, we're returning B times another instance, another recursive instance, M5, of, and frankly, I think it would be better if you just follow this one, like with the video. We'll do two more. We'll do this one, and then we'll do another one. So just watching. For people, same thing, watching this, just watch this rather than following it, and then do another one where you're actually writing it down. So, A minus 1. This next instance is going to be A minus 1, which is going to be 4, and then B. So let's do that. B times another instance, M5 of A minus 1, which is going to be 4, and the B is the same, 3. So what does a call to M5 sending 5 and 3 evaluate to? It evaluates to this. 3 times M5 of 4 and 3. That's the answer. That is the answer to that. Except that it doesn't help us because we don't know what M5 of 4 and 3 is. So we need to call another instance of M5, which takes 4 and 3. This one will remain on the stack unresolved, but we'll get back to it. We're going to work our way down, work our way back. So the question is, what is M5 of 4 and 3? Well, is A equal to 0? No. So we're not returning 1. Rather, we are returning, when we send these two, B times M5 of A minus 1, which is going to be 3 in this case, B, which is still 3. Which is fine, except that we don't know what M5 of 3 and 3 is. So we're going to have to figure that one out as well. And we ask, is A equal to 0? No. So we're not returning 1, we're returning this. We're returning 3 times M5 of, in this case, 2 and 3. And we're still not to 0, so we still don't know what that's going to resolve to. This 2 is not equal to 0, so we're not returning 1, we're returning this. We're returning 3 times 5 of 1, A minus 1. And 3. Fair enough, except, once again, is A equal to 0 for this call? No. So it doesn't return 1, it returns this. 1, 3 is going to return 3 times M5 of A minus 1, which is going to be 0, and 3. So finally, we reach a point when we say, okay, we got to evaluate this. It's going to be 3 times M5 of 0 and 3. What is M5 of 0 and 3? Well, when we do M5 of 0 and 3, we ask, is A equal to 0? Yes, it is. Right? So this all evaluates to 1. There is no other recursive call. Okay? This instance of 1 and 3 calls the recursive one with 0 and 3, but that resolves to 1. So now we can work our way back. We wanted to know what M5 of 5 and 3 is. Well, it's this. Okay, but what's that? Well, it's this. Yeah, but what's that? It's this. Yeah, but what's that? It's this. Yeah, what's that? It's this. Yeah, what's that? It is 3 times 1. So this is 3. So we can work our way back, and we'll do it the same way it's on the diagram. This is going to be 3. 3 times 3 is going to be 9. Which means that's 9. 3 times 9 is 27. That's 27, and 3 times 27 is 60, 81. Which means this is 81, and 81 times 3 is 243. 243. So 243 is the answer. And I could work my way down through one more time. If I did it one more time, if you get it, just stop the video. If you get it, stop listening. But what is M5 of 5 and 3? It's not 1, it's this. Okay. It's 3 times that. What's that? What's that? We work our way back and we know. Altogether, it ends up being through 1, 2, 3, 4, 5 returns, 1, 2, 3, 4, 5, popping out the stacks of other recursive instances of that method. We end up finally into that original one, and it knows that it's 3 times 81, which is 243.